Hi, welcome to the problem solving session on electric potential. So problem 1 that we looked at in class says consider a particle with a charge of Q equals 1 microcoulomb. Point A, which is a distance of 2 meters away from Q, and point B, which is a distance of 1 meter away from Q. If A and B in scenario A are diametrically opposite each other, as in figure A, what is the electric potential difference VA minus VB? Well, this is a point charge, so for any point charge you can calculate the electric potential value using KQ over R. So that means that the electric potential at point A minus the electric potential at point B would be KQ over D1 minus KQ over D2. We can factor K and Q out of that, and we're left with 1 over D1 minus 1 over D2 in the parentheses. And then we can go ahead and plug in numbers to solve for that. K is 8.99 times 10 to the 9th, though I think Mastering Physics uses 9 times 10 to the 9th. Newton meters squared per coulomb squared. The charge is 1 microcoulomb. .0 times 10 to the negative 6 coulombs. And then we have 1 over 2 meters minus 1 over 1 meter So let's see, 8.99 times 1 is 8.99. 10 to the 9th times 10 to the minus 6 is 10 to the 3rd. So this would be 8.99 times 10 to the 3rd, or 9 times 10 to the 3rd. In the parentheses, we have a half minus 1, so that's a negative 1/2. And that makes our final answer negative 4.5 times 10 to the 3rd. And the units here are going to be volts. It's not obvious necessarily looking at this, but a coulomb is going to cancel one of these coulombs. These meter units are going to cancel one of the meters, and I'm left with a Newton meter per coulomb. A Newton meter, you may recall from Physics 1, is a joule, and a joule per coulomb is the definition of a volt. So minus 4,500 volts here. And it makes sense that it's negative because I'm comparing a distance that's further away, and the further away I get from an electric potential, the lower the value of that electric potential. Part B asks, what is the electric potential difference if A and B are located as in figure B? So now we move B so that B is directly above charge Q rather than over on the left side of charge Q. But it turns out that doesn't do anything to change the answer here. Notice that electric potential is a scalar quantity. It's just a number. It can be positive or negative, but it doesn't have a direction associated with it like the vector quantities of electric force and electric field. So the distance that B remains away is still D2, and so this remains exactly the same for the electric potential difference in scenario B. In fact, you could trace a circle all the way around charge Q, and anywhere that you located point B on that circle, which would have a radius of D2, the answer would be the same. Contrast that, of course, with thinking about things like electric field. If you were asked to calculate the electric field at any of these points due to this, then it does definitely matter where things are arranged. Second problem we looked at was another point charge problem with 6 charges in a rectangular array. It says the figure shows a rectangular array of charged particles fixed in place with a distance of A equals 40 centimeters, and the charge is shown as integer multiples, of 3.4 picocoulombs and 6 picocoulombs. So if V is 0 at infinity, which is code for saying, hey, I can use my point charge relationship to figure out what the potential is, what is the net electric potential at the center of the rectangle? So right here. Well, again, the electric potential for a point charge is K Q over R, where R is the distance from that point charge to the location where I want to calculate the electric potential. And these are all scalar quantities, so I can just write a big sum of them. But in order to do that, we need to figure out, okay, how far are the corners from the center? And I'm just going to, with some foresight, call them a generic R right here. And also we need to know how far are those ones in the middle of the rectangle from here. And hopefully it's not too much work to see that those would be half the distance A if A is the full width of the rectangle. All right, so I'm going to write this out symbolically, starting at the top left corner and just going around the rectangle clockwise. So the V at the center of this arrangement is going to be, let's see, K times plus 2 Q1 over R plus K times plus 4 Q2 over A over 2, the center point, plus K times minus 3 Q1 over R plus K times plus 2 Q1, bottom right corner, over R plus K times plus 4 Q2 over A over 2 plus K times minus Q1 over R. All right, let's cluster the ones that have an R in the denominator and the others that have an A over 2. So I could rewrite this as K times, and then I've got plus 2 Q1 minus 3 Q1 plus 4 Q2, whoops, got the wrong one there, plus 2 Q1 minus Q1, and that's all over R, plus K, and then I'm going to get the ones that are over A over 2, so that's plus 4 Q2, and another plus 4 Q2, and their distance is A over 2. So let's look at the term that has the R in it right here. I've got plus 2Q1 minus 3Q1 plus 2Q1 minus Q1. All of that stuff in the parentheses sums to 0, which means I get no overall contribution to the electric potential from that first term. Things don't cancel in the second term, but we can reduce them a little bit. We can rewrite that as, let's see, 4Q2 plus 4Q2 is 8Q2. And then I'm dividing by A over 2, and you may recall from learning to divide fractions, you can invert and multiply. So dividing by A over 2 is the same as multiplying by 2 over A. I can rewrite this as 16K Q2 over A. All that remains is to plug in numbers for that. So I have 16, my Coulomb constant, charge Q2 is 6 picocoulombs, 6 times 10 to the negative 12 coulombs. and my distance, 40 centimeters. So that's 40 times 10 to the negative 2 meters. Punch that into a calculator. That one doesn't look as fun to do in your head. And I got 2.16 volts. The third problem we looked at in this set was back to the configuration of a parallel plate capacitor. It reads two large metal plates are 1.5 centimeters apart and have charges of equal magnitudes but opposite signs on their facing surfaces. Sorry, the focus was off on the camera. Take the potential of the negative plate to be 0. If the potential halfway between the plates is then 5 volts, what is the electric field in the region between the plates? Not at all required to draw anything here, but sometimes I think some of us got into physics teaching because we like doodling when we're doing the problem solving. So I got my two plates. One of them is negative, and it says, let's just arbitrarily assume that that electric potential is 0 there. Another one is positively charged, and we don't know what the electric potential is there. But we know that the electric potential halfway between the plates is 5 volts. And recall that equipotential lines in this geometry are parallel to the plates. So we can actually draw a whole line down the center of this, which is parallel to those two plates and is at a potential of 5 volts. What else? We know these are 1.5 centimeters apart. So there's a couple of ways I could proceed here. First of all, I'll just proceed with the given information. The piece that connects the electric field and the change in electric potential is that the electric field is equal to the negative of the change in potential over the change in position as you move along some path within that region. The negative sign simply tells us that if we're moving in such a way that our electric potential is going up, then the electric field is pointing opposite to the direction that we're moving. But if we're moving in a way that the electric potential is dropping, therefore delta V is negative, the negative negative gives us a positive E, and that tells us we're moving in the direction of the electric field. So the change in potential we know from here would be, sorry about that, would be negative 5 volts minus 0 volts, a 5 volt potential difference. And that distance would be half that gap distance. So I would end at, say, a position of 0.75 centimeters, starting at a position of 0 centimeters. And out of that I would get, let's see, 5 divided by 3/4 is 20/3. For those of you that don't like fractions, that would be approximately equal to a negative 6.7 volts per centimeter. The negative simply tells me that if I were to sketch the electric field, it would be back in this direction in this capacitor, because we got our values moving from the negative plate to the midpoint in this arrangement. You could also, by the way, note that because equipotential lines are evenly spaced throughout a capacitor, if I know the midpoint is 5 volts, then this plate right here has to be at 10 volts. And if you took a 10 volt potential difference over the full distance of 1.5 centimeters, you would find the exact same value for the electric field. Finally, we looked at 3 different geometries of, well, I guess they're all the same geometries. They're all parallel lines. So again, these would be electric fields in some, equipotential lines in some region where the electric field is fairly uniform, since these equipotential lines are parallel to each other. The problem reads, the figure shows 3 sets of cross sections of equipotential surfaces in uniform electric fields. All 3 cover the same size region of space. So that's code for this distance right here, whatever that is the same in all 3 of these pictures. The electric potential is indicated for each equipotential surface, so rank the arrangements according to the magnitude of the electric field present in the region, greatest first. So notice this one ranges from 20 volts to 100 volts. This one ranges from negative 140 volts to negative 100 volts, and this one's negative 10 volts to negative 50 volts. Well, magnitude of the electric field would rank according to the magnitude of the potential difference over the distance, but we're told that the distance is the same in all of these. So really we're just looking at the potential difference top to bottom. And so the potential difference in scenario A, top to bottom, is 80 volts. The potential difference top to bottom in scenario B is 40 volts. Potential difference in scenario C, top to bottom, is also 40 volts. And that gives us our ranking for part A here. This must mean that scenario 1 has the greatest electric field, and that is greater than scenario 2, which is equal to scenario 3. B asks, in which is the electric field directed down the page? Well, again, electric field points from regions of high electric potential to low electric potential, and electric field lines or electric field vectors are always perpendicular to equipotential lines or equipotential surfaces. So in scenario 1, high potential is at the bottom, lower potential is at the top. The electric field lines would look something like this. In scenario 2, negative 100 volts is a higher electric potential than negative 140 volts. So the electric field vectors would again point from the bottom to the top. If I was trying to be diagrammatically consistent, I would draw fewer of those vectors to indicate a weaker electric field, since there's a smaller potential difference. Here in scenario 3, minus 10 volts at the top, minus 50 volts at the bottom tells us that the electric field in scenario 3 actually points down, and that gives us the answer to B, in which is the electric field directed down the page. That is scenario number 3. All right, this concludes the problem-solving session on electric potential that we did in class. As always, if you're watching this video and you notice an error in any of the problem solutions, I would appreciate you letting me know about that. Thanks.